Hello everyone, in the graph part 1 we have seen water graphs, concepts involved in graph, and we have seen how we can represent a graph using 4 different methodologies. In graph part 2 we have seen different graph traversals like BFS, TFS, and how a graph can be divided into different components. And in graph part 3 we have talked about what is a cycle, how we can detect a cycle, what are the algorithms that we use to detect a cycle in both directed and undirected graph, and after it we have talked about what is a topological sort and Kahn's algorithm. In topological sort we have talked about Kahn's algorithm. Now in this session we are gonna learn two important algorithms which are really important whenever you are talking about graphs in general, and you will find these two algorithms in competitive platforms, in actual coding rounds, and in many other hackathons kind of things, right? Whenever you are dealing with graphs in DSA, these are the two most important algorithms that you have to know. And along with that, it is one of my favorite algorithms, Dijkstra's and Bellman-Ford algorithm. Now let us talk about Dijkstra's algorithm. So both Dijkstra's and Bellman-Ford algorithms are used to find the shortest path between a source node to all the corresponding vertices. For example, let's say that in a graph I am having 10 nodes, and one of them I'm considering that as a source node. Now from this source node to all of the rest of the 9 nodes, I need to find the shortest path. For example, let's say for the second node there are two possibilities, there are two paths through which I can go from my source node to the second node, but I need to choose the shortest path. And that thing, if I am doing that, then that thing is known as Dijkstra's algorithm. This is the basic motive of Dijkstra's algorithm. Dijkstra's algorithm will give you a shortest path between a source node to all the corresponding neighbor nodes to all the corresponding nodes in a graph. This is the main work, this is the main motive of Dijkstra's algorithm. And one more thing is that Dijkstra's algorithm is based on greedy approach. Whenever you hear the word shortest, largest, minimum, maximum, then you should get the concept of greedy algorithms in your head, right? And in greedy algorithms, what we generally do at each and every level, we will find out the local solution, and after finding all the local solutions at each and every level, according to our priority, according to our need, we will differentiate the solutions, and whatever the best solution that we are having among these local solutions, we will make that solution as a global solution. This is the basic working of a greedy approach, right? Similarly, here also we are gonna follow the same thing. For example, let us consider that I am having a component like this. A component 0 is connected to 1 and 1 is connected to 2, and something like this. I am having a structure like this, and the weight is 2, 1 and 4. Now my source node is 0 and I have to travel from 0 to 2. Now if you observe, from 0 to 2 there are two paths. This is path 1 and this is path 2. Now my question is, what is the cost? Cost is nothing but the total edge lengths which are lying from source node to my destination node, or whatever the corresponding node you wanna calculate. Whatever the edges which are lying in between these two, and what are the values of that edges, the sum of values of that edges is nothing but cost of that particular path. So if I talk about the path 1, the cost of path 1 will be 2 plus 1. So the cost of path 1 will be 3. Okay, now for path 2, this is my source node, this is my destination node, right? And you can see that there is only one path, there is only one edge connecting these two, and the cost of that edge is 4. So for path 2 the cost will become 4, and for path 1 the cost is 3. Now this is my local solution 1 and this is my another local solution 2, but in Dijkstra's we are calculating the shortest path. Right? So I will consider 3 as my final solution, or you can call it as a global solution. Like this, I will first of all calculate for this node. For example, this is my source node and this is the node I want to calculate the distance. So you can observe that this can be one of the paths. Like this I can go, and this is the another path. These are the two node paths that can be possible for this two nodes. And if I calculate the cost of path 1, let's say this is my path 1 and path 2, so the cost will be 2 plus 7, that is 9, and cost of path 2 will be 1, that is 2 plus 1 plus 3 plus 2. So this thing will give me 4, 5, this thing will give me 8. Now my question is, which one is the least? The least value will become my shortest path. So the shortest path between 0 to 3 will become 8. Like this, what I will do is that for two corresponding nodes, I will try to calculate all the possible paths cost, and after calculating all the possible path cost, I will take the value which is minimum in terms of numbers, right? Which is minimum, I will take that. This is my greedy approach. Now let us talk about the logic. I hope you have understood the approach. We are gonna use the greedy approach. Now let us talk about what is the logic of greedy, what is the logic of Dijkstra's algorithm. So let me erase all this. So the logic, to understand the logic, here I am considering a simple structure. Let's say that I am having a structure like this: 0 is connected to 1 and 1 is connected to 2. Okay, and let us say that the weight is 2 and the weight is 4. Now what I will do is that, first of all, Dijkstra says that from the source node, whatever all the nodes, all the vertices, you need to calculate the shortest path. This is our main motive. This is the main work of Dijkstra's algorithm, right? So here I need to calculate the distance between 0 to 1 and 0 to 2. And here the logic says that if there is a direct path and it is the only path, if this is the case, then what I will do is that I will make that path as my shortest path. Here you can see that I am having only one path, and it is a direct path, and it is the only one path. I am not having any alternative paths. If that is the case, then I will make the shortest distance between 0 to 1 as 2. Now the second logic says that if you don't have any direct path, then you need to perform these steps. That is, first of all, initialize the distance of that node as infinity. So I will initialize the distance. Initially I will initialize the distance between 0 to 2 as infinity. So I will initialize the distance as infinity. Now after initializing the distance as infinity, the step 2 will be calculate its corresponding weight. Here I know the distance of these two. Let's say that this node as u and this node as v. Now I know the distance of u, which is nothing but from source to my u node. This is my source, right? So from source to my u node, the distance is 2. I know the distance, and I know the weight between u comma v. That is, I know the distance of u, and I know the distance, the weight, the edge length between u comma v. If I know these two things, then I will calculate its sum. So the first step is, this is my v node, right? This is my v node. So I will make the distance of v initially as infinity. Now the second step is, I know the distance of u. This is u. This is distance of u. That is 2. And the weight, I already know the weight of u comma v, which is the edge length connecting the u node and the v node. Here let me write it here. The 1 is connected to 2 and 2, okay, 0 is connected to 1 and 1 is connected to 2, and this is my source node, u node and v node, and I don't know the direct distance between distance of v, but I do know the distance of u. This is my distance of u, and this thing is my weight of u comma v. So if I know the weight of u comma v and distance of u, then here the distance of u comma v is 4. Then what I will do is that I will try to calculate distance of u plus weight of u comma v. Here you can see that 2 plus 4, it is giving me 6 as the answer. Now the third step is try to compare distance of v, whether the distance of v is greater than this value, which is 6, which is the sum of these two, distance of u plus weight of u comma v. If the sum is less than distance of v, what is the distance of v? Here you can see that the distance of v is infinity, and infinity is greater than sum of distance of u plus weight of u comma v. If I am reaching this condition, then I will make distance of v, this is my fourth step, that is distance of v is equals to distance of u plus my weight of u comma v. This is what I am doing. This is the logic of Dijkstra's algorithm. So here, let me write it here. This is the structure I have extracted, right? 1 is connected to 2, 2 is connected to 3, and the weight is 2 comma 4. Now this is my source node, u node, v node. Now what I did is that if I don't have any direct connection, here you can see that for 1 and 3 I don't have any direct connection. So if I don't have any direct connection, then I will make it distance as infinity. So here the distance is infinity, but I do know the distance of u. The distance of u is the value this one, so the distance of u will become 2. Okay, now I know the weight of u comma v, that is 4. So what I will do is that if I know these two values, then I will sum these two, that is 2 plus 4. This thing will give me 6. Now after calculating the sum of distance of u plus weight of u comma v, after calculating this, I am comparing whether the distance of v, which is infinity, is greater than the sum of these two, which is 6. If this condition is true, then what I will do is that I will change the distance of v is equals to distance of u plus weight of u comma v. This is what I am doing. So I will change from infinity to distance as 6. Like this I will calculate. This is the main logic of Dijkstra's algorithm, and if you didn't get the logic, then I will urge you guys to go back and see the video again. Okay, so here my final distance of each and every node will become 1 is connected to 2, 2 is connected to 3, and the shortest path between 1 and 2 will become 2, and the shortest path between 1 and 3 will become 6. 2 and 6, and the shortest path between 1 and 1 remains the same. So I am coming source node to the source node again, so the distance here will become 0. Like this I will calculate. Now let me do a simple dry run. I will do for the given graph which I am showing you in the diagram. I will try to perform dry run for at least 3 nodes. If I perform dry run for all the nodes, then the explanation will become 30 minutes. So I don't wanna make this kind of long video. So I will show you the dry run, how the code is working, how our logic is working for at least 3 nodes, and after that I will talk about how we gonna perform or what is the code of this Dijkstra's algorithm. So let me show you a dry run. So initially this is my source node. Except source node, I will assign all the corresponding node distances as infinity. So I will assign the distance as infinity, 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 infinity. Now after assigning all the corresponding neighbor nodes distance as infinity, I will make the source node as my u node. Here this will become my u node, and this thing will become my v node, and the distance of u here in the first iteration, the distance of u will become 0, distance of v is infinity, and the weight of u comma v, you can clearly see that the weight, which is nothing but the edge length between u and v, which is nothing but 0 and 1, is 2. Now I will calculate distance of u plus weight of u comma v. U comma v, here you can see that the answer I am getting is 0 plus 2, so it will give me 2 as the answer. And after calculating this, I will check whether my distance of v is greater than distance of u plus my weight of u comma v. Right, here you can see that infinity is greater than 2. If this is the case, then I will change the value of distance of v is equals to distance of u plus weight of u comma v. like this I will change the value of distance of v. So here I will change the distance of v as from infinity to the sum of these two, which is nothing but 2. So the shortest distance between 0 and 1 will now become 2. Now after that I will change the v node. My v node will become this. Now in the second iteration the distance of v will become infinity again. Here you can see that for this v node the distance is infinity. Now here the distance of u will remain the same. So u is 0 and weight of u comma v is now 4. Now I will calculate the sum 0 plus 4, which is nothing but 4, and distance of v is infinity. Here you can see that infinity is greater than 4. If this is the case, then I will change the value of distance of v is equals to the sum of these two. What is the sum of these two? 4. So I will assign the value as 4. So here I will change from infinity to 4. Okay. Now for u node, which is my source node, I have visited all the neighbors. For u node, its neighbors is 1 and 2. If I have visited the neighbors of u, then I will now change the value of u. So let's say that I am changing the value of u to this. So this one node will become my new u and my new v will become this 3 node. So in the third iteration, the distance of u is now 2 and the weight of u comma v, here the u node is 1 and the v node is 3. So the distance is 7 here, and the distance of v from my source node, here this is my source node, right? So from the source node to my v node, what is the distance? I don't have any direct distance, and if I don't have any direct distance, then I will make it as infinity. So here I will make this as infinity. Okay. Now after this, what I will do is that I will check the sum of these two, that is 2 plus 7, whether the value which I am getting is less than infinity. If this is the case, then I will change the distance as 9. This is what I'm gonna do. This is the overall pseudocode, or you can say dry run, of my Dijkstra's algorithm. Now let us talk about the pseudocode of this Dijkstra's algorithm. So talking about the pseudocode, what I will do is that first of all I will create a pair class, and in the pair class I will store the node value, whatever the node I am at, and the path related to. For example, let's say I am at 1. So for this node, what is the shortest path? The shortest path is 2. So I am gonna pass the shortest path, right? And this pair class will compare the first path, the path which I am passing, and the alternate path. Here you can see that there is no alternate path. If there is no alternate path, then that thing, whatever the path, single path I am having, that thing will become my final solution. So the pair class is used to compare paths. Okay. Now second step is that I will, in the main function, whatever the function I am creating, let's say I am creating a Dijkstra's algorithm function. So in that function I will initialize all neighbors with infinity. Now after initializing all neighbors with infinity, what I will do is that I will create a priority queue of pair class, and in this priority queue I will add elements according to the path priority. The element which is having the least path, I will add that in my priority queue. This is the basic logic, and when I show you the code of Dijkstra's algorithm, it will become super easy to understand. So let us talk about the code of Dijkstra's algorithm. So in the program, first of all, here I have created a class. First of all, I am importing my java.util.star. After that, I have a universal class called as classroom, and in that, first of all, I have created a class h, and in the h, what are the things I am having? Source, destination, and the h value, and basically I am creating a constructor to initialize these values. Now after that, I am creating create graph, and in the graph I am creating the graph which we have dry run. So this is the graph I am using, right? So I am creating the same graph in my create graph function. Okay, now what I will do is that first of all I will define my pair class. So I will write my class static class pair, and in the pair class what I will do is that I will write int n, which represents the current node I am at, and after that my path for this current node, what is the optimal path, right? And I will write a constructor public my pair, public pair. Here I will pass my int n and int path, okay, and I will basically initializing this dot n is equals to n and this dot path is equals to path. Now after this, what I will do is that I will write a comparator on what basis my priority queue is working. So I need to give on what basis my sorting internally should happen in my priority queue. So what I will do is that I will write override function. So override, and in this, first of all, I will create public int compare to. Here I will pass on the basis of path, because in the Dijkstra's algorithm I am calculating the shortest path. So in the priority queue, whatever the priority queue I am creating, I will add elements in my priority queue based on the path. So the sorting will happen based on the path. So here I will write my pair P2, I will pass my pair P2, and I will return the priority based on my path. So this dot path minus P2 dot path, I am returning basically my path node. Now after writing the function, let me write the function called as Dijkstra's algorithm. So let me define my Dijkstra's algorithm. So public let's say void, public static void Dijkstra's algorithm. Here I will pass my graph array list of h. I will pass my graph and my source node. So graph and my source node. Now first of all, I will create a distance array. In this I will store all the distances. For 0 node, what is the minimum distance? For 1 node, what is the minimum distance between source and this one node? For 2, what is the distance between 0 to 2? For 3, what is the minimum or optimum distance between 0 to 4? Like this, in this array I will store the shortest paths, okay? So path is equals to new int of graph.length. Now after this, what I will do is that I will initialize all the nodes with infinity. So int I is equals to 0 and I should be less than graph.length and I plus plus, and I will initialize all the elements with plus infinity. So distance of I is equals to my integer dot max value. I am initializing with plus infinity. Now after this, I will create a boolean visited array. In this I will write boolean of new boolean graph.length, and this will keep track whether the element is visited or not, and I am using a priority queue in this, right? So I will write priority queue, and in this I will pass my pair class. So pair, let me give pq is equals to new priority queue. Now after this, what I will do is that I will add pq.add my pair. I am adding my source node. So I will add my source node and its corresponding path as 0, because the path between source node to source node is 0. Now after this, what I will do is that it is showing some kind of error. The method priority queue is not applicable. Why it is showing error? Let me check. Okay, here I need to give new pair. Okay, new pair of source comma 0, because this is not a primitive data type, right? Here I am passing my path, okay, my pair. That is why I need to create the object of pair, and like this I will add elements in my priority queue, because in the priority queue I am not storing primitive data type, I am storing pairs. Okay, now here what I will do is that I will run a loop. While my priority queue is not empty, pq dot is not empty. What I will do is that I will write pair current is equals to pq dot remove. I am removing whatever the current node I am having in my priority queue, whatever the element I am having, I am removing it. Now if that element is not yet visited of my current dot path, if this is not yet visited, then I will make this as visited of current dot n is equals to true, right? Now after this, what I will do is that I will run a loop for int I is equals to 0 and I should be less than my graph of current dot n dot size and I plus plus. In this, what I will do is that for all the neighbors, I need to calculate for this node what are the nodes it is attached with, whatever the neighbors it is having. I need to calculate the shortest path, right? So I will get all the neighbors. HE is equals to my graph of current dot n dot get ith element. Now after getting the ith element, I will calculate int u will become my e dot destination and int v will become my, sorry, here u will become source and v is equals to e dot destination. Now int weight is equals to whatever the weight, e dot weight I am having, I am calculating it. Now I will check my formula, that is if my distance of u, here I need to give distance, dis of u is plus my weight is less than distance of v. If this is the case, then what I will do is that I will change the distance of v value is equals to distance of u plus my weight. Like this, I will overall calculate the overall path, the shortest path between my source node to my next corresponding node. Okay, now here I will print all the paths. So let me write here for int I is equals to 0 and I should be less than distance dot length and I plus plus. In this, what I will do is that system.out.print and I will print distance of I plus some space, like this I will print. Now in the main program, let me here pass my Dijkstra's algorithm and here I will pass my graph and my source node, and let me save and run this. Here I need to give, okay, where is the error? Okay, this is the error. Now let me save, and so let me save this and run here. It is showing some kind of error, method does not over implement. Okay, so in the class, in the pair class, we need to write here, where is my pair class? Here I need to write implements comparable interface. So comparable, and here I need to pass my pair. So this pairing, this like sorting will happen based on the path, right? And in order to perform my like comparison, I need to implement my comparable interface. Okay, so let me save this here and run again, and if I run this, then whatever the graph I have created, this is the graph I have created, right? So for this graph, the source node is 0. So from source node to all the corresponding vertices, whatever the shortest path is there, my output will print it. So let me save this and run. So you can see that I got the output now, which is the shortest path between 0 to 0 is 0. The shortest path between 0 to the next node is 2, and the further nodes 3, 8, 6, 10. Like this, I will calculate the shortest path using Dijkstra's algorithm. But there is a catch in Dijkstra's algorithm. That is, the algorithm which we have studied will not work for negative values. For example, let's say in a graph, we are having negative values. The h value, the weight which we are having is negative. In first session, I have shown you that the graph weight, in the graph, the weight values can be negative as well. And if I am getting a negative value, then you need to remember that Dijkstra's will not work. And in that case, we use another algorithm, even though it is kind of slow when compared to Dijkstra's is very fast. When compared to Bellman-Ford, Dijkstra's is fast. But Bellman-Ford will work for both negative values and positive values of the given graph. Whatever the weights might be, my Bellman-Ford algorithm will work. So let us talk about Bellman-Ford algorithm. Now talking about Bellman-Ford algorithm is also used for the same purpose. The purpose of Bellman-Ford is that there is a source node and there are other nodes. You need to calculate from the source node to all the corresponding vertices what is the shortest path. What can be the shortest path among n paths? Which one is shortest? This is the work of Bellman-Ford and Dijkstra's algorithm. But the problem with Dijkstra's algorithm is that Dijkstra's algorithm will not work for negative values. Let's say that in the weights, here you can see that I am having weight as -4, I am having weight as -1, and if I am having the weight values as negative values, then the Dijkstra's algorithm which we have studied now will not work, and in that case we will use Bellman-Ford algorithm. And Dijkstra's algorithm is based on greedy approach, right? We use greedy approach, and Bellman-Ford algorithm is based on DP approach, which is dynamic programming. I will give you a complete material of dynamic programming, and by just reading it, I'm like very sure that you guys will understand. Okay, so I will provide you there are 10 classical problems in dynamic programming, and along with that I will provide you the reading material of dynamic programming in 1 or 2 days, hopefully whenever I launch this video. Along with that I will provide you the material of dynamic programming. Okay, so dynamic programming is a concept. You can consider it as an alternative. When greedy fails, we use dynamic programming there. Generally, not in all the cases, but around 80 to 90% of cases, whenever greedy approach fails, we use the approach of dynamic programming. And in the material which I have provided you, which I will provide you surely, in that we have seen in that I have shown you how dynamic programming works. Okay, so here what I will do is that I will create a two-dimensional array. Let's say that this is the array I am creating, and on the x-axis I represent nodes, on y-axis I will represent the number of iterations, right? Now let me represent the nodes here. I am having 0, 1, 2, 3, 4, right? So what I will do is that I will follow the same approach initially, except the source node I will assign the distances of all the nodes with infinity. So here the distance of this will become 0, infinity, 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 and at each and every iteration I will store in the boxes, I will store the distances. So from 0 to 0 the distance is 0, and from 0 to 1 initially at 0th iteration the value is infinity, 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 infinity. Okay, now in the first iteration I will try to calculate the same thing. Here we will use the same formula, that is I will run a loop for my all the elements, v minus 1 elements. I will run my loop and I will try to calculate whether the distance of u, let's say this is my u node, this is my v node, right? If the distance of u comma v, here let me write the table here, let me construct, and I will show you in the process of constructing table, I will along with that I will show you the dry run also. So here this is the nodes I am having, right? 0, 1, 2, 3, 4, and these are my iteration: 0th iteration, first iteration, second iteration, third iteration. Here total number of nodes are 5. So here the total number of nodes are 5, and I will perform v minus 1 iterations. So I will perform 4 iterations, and the value at the very last iteration in the table, whatever the values I am getting, that thing will become my shortest path in my Bellman-Ford algorithm. Okay, so I will run my loop for up to from 0 to 4 iterations. Okay, now here at the 0th iteration I will initialize. The 0th iteration is nothing but initialization step. We don't generally count the 0th iteration as a actual iteration, because in the first iteration, in the 0th iteration, I am assigning all the nodes with infinity. So here I will assign all the things with 0, infinity, 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 infinity. So 0, infinity, 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 infinity. Now here this thing, initially the 0th node, which is my source node, will become my u value, And this, let me remove this. I don't wanna make a mess here, and if I make a mess then you guys will definitely get confused here. So let me remove all this here. Let me make it very simple to understand, okay? So at the initial stages, the source node will be my U node, okay? Now if I make this V, the first node, as my V node, then what is the distance? The distance from 0 to 2 is, distance of U is 0, weight of U comma V is 2, and distance of V is infinity. And if infinity is greater than the sum of these two things, then I will change the distance of V from infinity to 2. So at 0, the distance of 0 to 0 will remain the same, 0, 0, 0. At each and every iteration, the distance between 0 to 0 will remain 0, right? So I don't need to check for the first node. Now for 0 to 1, I have calculated from this formula. We call this formula, I need to remember that we call this formula as relaxation step. So for V minus 1 times, whenever I am running a loop, I will calculate the relaxation step, and if the relaxation step is getting satisfied, then I will change the distance of V, okay? So here initially the distance of V is infinity. Now after calculating the relaxation step, my distance of V will get changed, and I will change the distance from infinity to 2. So here I will change the value of 0 to 1 as 2. Now I will come to this node. So here you can see that the shortest distance from 0 to 2 is 4, okay? So here I will write 4. Similarly for 0 to 3, here you can see that there is only one path. I can go from 0 to 2, from 2 to 3. If I wanna move from 0 to 2, then 2 is the middle wire, 2 is the middle element here, okay? So the distance will become 4 plus 2. Here the distance will become 6. Now after this 0 to 4, so here you can see that I have only one path again, that is from, I can go from 0 to 2, 2 to 3, and 3 to 4. So the distance here will become, the distance will become 4 plus 2 plus 4. So the distance will become here 10. Now I have calculated in the iteration 1, I have calculated all the paths, and you can observe that I have chosen only one path, and there can be n number of paths between two nodes. So again within the iteration 1, I will check whether there is another path for any nodes. Here you can see that for node 2 there is an alternate path. For node 2, this is not the only path I am having, this is alternate path. So I will check in the iteration 1, I will check the value of alternate path. So the value of alternate path is 2 minus 4, this gives me minus 2. So I will change this 2 value as minus 2. Now if I am not choosing this path to travel from 0 to 2, then I should not choose the same path in order to travel from 0 to 3, right? I hope you are getting it. I hope you guys are getting it. And if you are a beginner, if you haven't read anything about Bellman-Ford algorithm, then I'm sure it will haunt you. You will not understand anything else, right? But believe me, if you try to understand it, if you watch the video again and again, if you read the documentation, I'm very sure you guys will understand it, okay? So here I'm choosing the alternate path. So in order to go to 3, I'm not choosing this path, I'm choosing this alternate path, okay? So for this alternate path, the weight here will be minus 2 and here 2. So the minimum cost will become 0. Now if I'm not choosing this path to travel force, I'm choosing this path, okay? I'm choosing this path. This might be a little bit confusing, but the main motive is that within the first iteration, I have calculated for one path, these are the values 0, 4, 0, 2, 4, 6, 10. And if I'm choosing an alternate path which is available within the iteration 1, if I'm getting a optimized value, so I'm getting a less value, then I will change my path, right? So my answer will become 0, 2, -2, 0 and 4. So here I will change it from 4. So my iteration 1 is completed. Now the graph which I am having is 0, 0 is connected to 1, 1 is connected to 4, 4 is connected to 3, 3 is connected to 2 and 2 is connected to 1, like this. Okay, and it is connected, let me give the directions also. Yep, yeah, like this. Okay, and the distance from 0 to 0 is 0, 0 to 1 is 2. Observe the table, from the table we are getting the values, and 0 to 2 is 2, sorry, -2, and 0 to 4 is 4, and 0 to 3 is 0. These are the possible shortest distance that can be possible. Now in the first iteration I will perform the same step, the same relaxation step, and if the graph is not divided into components, then I will get the same answer. So in the second iteration also I will get the answer 0, the same answer, 0, -2, 0, 4, 2, -2, 0, 4, 2, -2, 0, 4. Like this I will get the answers like this, right? And I hope you have understood the approach, what we are doing. So basically I am running a loop, and in the loop will run v minus 1 time, and within that I am checking my relaxation step. If in the relaxation step the condition is satisfying, then I am changing the value of the distance of v. Now when we code this thing, believe me, it will become super clear to you guys. So let us talk about the code of this algorithm. So here let me create a function, public void, public static void Bellman-Ford. Here I will pass my graph, array list of h graph, and my source node, into my source node. Right now what I will do is that I will follow the same thing, but here I am using the DP approach. In Dijkstra's algorithm I am using greedy approach. Here I am using a dynamic programming approach. So here I am creating the same destination array. Destination is equals to new int of graph.length. Now after that what I will do is that my first step is initialize all the elements with +infinity. So for int I is equals to 0, and I should be less than my distance dot length and I plus. In this what I will do is that if my I is not equals to my source, then I will initialize distance of I is equals to integer dot max value. Right now after running my initialization step, I will write here int v is equals to my graph dot length. Whatever the graph I am having, I am taking the length of that graph. Now after that I will run a loop for int I is equals to 0, and I should be less than my v minus 1 and I plus. Here what I will do is that first of all I need to calculate the source node, and for this source node whatever the corresponding edges I am having, I need to calculate it. So here for edges I will run a loop for int I is equals to 0, and I should be less than my graph dot length and I plus. Now here I will run a loop again for int j is equals to 0, and j should be less than my graph of I dot length. Here in the second loop I am trying to calculate the edges. Here I need to give size, right, and j plus. Okay, now within the loop first of all I will calculate edge e is equals to graph of my j dot get ith element. Get here I am already using I, so here I will give j plus, and in this I will give k plus plus, j and k. Okay, so here I will give get kth element. Now after calculating my h, I need to calculate u, v, my weight. So int e is equals to int u is equals to e dot my source node. Now int v is equals to e dot my destination node, and int weight is equals to my e dot weight. Okay, and here I have already assigned, let me give here capital V instead of small v. Where is my size? Okay, instead of small v I will give capital V, because I can't use a variable more than one time. Okay, now what I'm gonna do is that after calculating this, I will perform my relaxation step. In the relaxation step, I will check if my distance of u is not equals to, if my distance of u is not equals to my integer dot max value and my distance of v, this is my actual relaxation step, distance of u plus my weight is less than distance of v. If this is the case, then what I will do is that I will change the distance of v value. Distance of v is equals to distance of u plus my weight. Like this I'm gonna do, and finally after calculating all the shortest path, I will print int I is equals to 0 and I should be less than distance of distance dot length and I plus plus. And here I will print system dot out dot print my distance of ith element. Like this I will print. I hope you have understood. So in the program, what I am doing is that first of all I have created my distance array. Now I am initializing all the things with a plus infinity. Now in the program you can see that I am running 3 loops, but the catch here is that the time complexity of this program will become big of E, which is nothing but the total number of edges which are present in my graph, right? The time complexity of program will become big of E, okay, and E represents the total number of edges present in my graph. Okay, so here first of all I am calculating the size of the graph, and for all the nodes, for all the edges, I am calculating u value, v value, and I am checking my relaxation step. If my relaxation step is satisfied, then I am changing my distance of v value, that's all, right? And let me, in the place of Dijkstra's algorithm, let me print Bellman-Ford algorithm. And if I give the same graph which I have created here, the output will be the same, the output will not change. So let me save this and run again. Here you can see that we got the same output as we did in Dijkstra's algorithm. Whatever the output we got, we are getting the same output here. So if I print here Dijkstra's algorithm, and if I run this code, then these two will give me the same output. Here you can see that. Let me print also a next line here, system.out.print. Okay, so let me save this thing and run. So you can see that the Dijkstra's algorithm, this is the output of Bellman-Ford algorithm, and this is the output for Dijkstra's algorithm, and both are giving me the same output because I am running this for the same graph. This is the graph I have created, right? And I am running the same graph, 2 algorithms, and 2 algorithms are built for the same thing, but the only difference is that Dijkstra's algorithm will not work for negative elements, and Bellman-Ford algorithm will work for edges which are having negative values as well. But when compared to Bellman-Ford algorithm, Dijkstra's algorithm is little bit efficient, right? In terms of time complexity, it is efficient. Okay, so up to now we have studied what is Dijkstra's algorithm, what is Bellman-Ford algorithm, 2 important algorithms in graph theory. And I know that at the very initial stages it is very tough to understand, right? And these are the algorithms, these are the sort of concepts where you cannot understand in one go. By just listening to this you will not understand. You have to put your time and effects into understanding that, and when you put your own time and effect in learning things, then believe me, you will learn it. And I will give you the resources, I will provide you the websites from which I am using this concepts, and believe me, you will like learn it. And yeah, at the very initial stages I accept that these two algorithms are kind of tough, but with time these two are very simple, logical, and very easy to understand algorithms. So in the next session we are going to talk about a concept called as minimum spanning tree, and based on minimum spanning tree we have two more algorithms called as Prim's algorithms and Kruskal's algorithms. So in the next session we will see what is Prim's algorithm, what is Kruskal algorithm. So with that being said, I will see you in the next one.